Welcome to the Survey of Mathematics. I'm Jeremy Pletcher, the author of Survey of Mathematics. This is lesson 1.9 where we'll be dealing with fractions, where we're going to convert fractions into decimals and vice versa. So to begin our lesson today, we're going to look at changing fractions into decimals. This is a fairly simple process. In order to change a fraction into a decimal, I'm going to divide the numerator by the denominator. When that happens, I could have a value that stops. We call this a terminating decimal. For instance, 1/2 would give me 0.5. So there are no digits that keep on repeating. It doesn't go on forever. It ends or terminates, and therefore it is called a terminating decimal. Another example is 5 divided by 8. When we take 5 and divide by 8, we get 0.625. But there is where it ends. So we don't have any values after the 5. It terminates, therefore it is a terminating decimal. If we divide the numerator by the denominator and we have digits, either a single digit or a group of digits that repeat, we call that a repeating decimal, and it continues on indefinitely. For instance, 1/3. If I take 1 and divide by 3, I get 0.33333, and it continues on. 2/3 is the same way. And there can be multiple values that actually repeat, not just a single value. For instance, if I take 5 and divide by 7, I get 0.714235, 714235, 714235, and those 6 digits continue to repeat over and over again. Both of these would be considered repeating decimals because they have one or multiple values that are repeating in the same order. Decimals that continue without repeating are called irrational numbers. Values such as pi. Pi, as far as we've taken it out, has not have any values or patterns that continue to repeat the same numbers over and over again. So this would be considered an irrational number. We're going to talk about that in the next section. So why don't we try converting these fractions into decimals? Let's begin by taking 1/5. Now you are welcome to use a calculator. If we take 1 and divide by 5, we get 0.2. I always encourage my students to memorize the values that have fractions that have a denominator of 2, 3, 4, 5, 6, 8, 9, and 10. Those tend to be very, very commonly used, and most of them are fairly easy to remember. But 1/5 is equal to 0.2. What about 3/10? Well, if I take the numerator, the 3, and divide by the denominator of 10, I'll get 0.3. With a base 10, I can also just move the decimal point over one place value, and that would also give me the 0.3. How about 2/3? Well, if I take 2 and divide by 3, I will get 0.6 repeating. So if you remember that 1/3 is 0.3 repeating, we're simply doubling that, and so it's going to be 0.6 repeating. We can indicate a repeating value either through an ellipsis, such as 0.666 and then 3 dots, or a bar over the number or set of numbers that repeats. If you have multiple numbers that repeat, it really is better to use the bar rather than the ellipsis. What about 7/5? Now this is an improper fraction, so we should have some sort of whole number out in front of our decimal. So if I take 7 and divide, I will get 1.4. Now we could have changed it into a mixed number first, 1 and 2/5, and then simply figured out the decimal equivalent of 2/5. But in this particular case, that takes more time than just doing it on a calculator, so we take 7 divided by 5 and we get 1.4. So that brings us to the second part of our lesson, and that is changing from terminating decimals into fractions. So if I have a terminating decimal, such as 0.2, how do I get it back into a fraction? So the first step is you want to remove the decimal point. So as the example of 0.2, I remove the decimal, simply making it 2. Then my next step is to place the number in the numerator of my fraction. So in my example verbally, I used 0.2. I removed the decimal to make it 2. The 2 goes in the numerator. In the example I have up here on the board, we have 0.25. I removed the decimal to make it 25. That 25 would go in the numerator. Then in the denominator, I'm going to write a 1 followed by the number of zeros that I had decimal values in my original number. So verbally, I was saying I had 0.2. That is only one decimal place over, and so I'm going to have 2 over 10. In the example I have up here on the board, 0.25, that is 2 decimal places, so I place a 1 with 2 zeros after it, and I get 25 hundredths. Then we're going to go through the process of reducing, which we covered in an earlier lesson. So if we reduce 25 hundredths by a factor of 25 over 25, I get 1/4. So 0.25 is equal to 1/4. Most students remember this one. If you have 25 cents, you have a quarter, or 1/4, of a dollar. So try some of these. Let's say we wanted to convert 0.4 into a fraction. Well, I begin by removing the decimal point, making it 4. I put that 4 in the numerator, and then in the denominator, I'm going to put a 1 followed by the number of decimal values that I had in my original answer. So if I had 0.4, that is 1 decimal place, and so I have 4 over 1 with 1 0. If I reduce 4/10, I get 2/5. What about 0.125? Well, I remove the decimal, making it 125. It has 3 decimal place values in it, so I'm going to put 125 over 1 followed by 3 zeros, which of course is 1,000. When I reduce that, I can reduce by a factor of 125 actually, but if you didn't see that, most of you can see that you can reduce by a factor of 25, which would give you 5 over 40, and then you can reduce 5/40 down to 1/8. Eventually you get to the same answer, that of 1/8. What about 0.092? Well, I remove the decimal and I put my number up in the numerator. So that's going to be 92. I really don't need that 0 in front. Just the 92 will work for my numerator. In my denominator, I have a 1 followed by 3 zeros. You do need all 3 zeros in this number to make it 1,000. So that gives me 92 over 1,000, and that reduces down to 23 over 250. As our final example, let's say I have 1.39. I have a mixed number. Well, I can leave that 1 out in front. That's going to be my whole number of my fraction, and I can just deal with the 0.39. I put 39 in the numerator and then 100 in the denominator because 39 has 2 place values, and so I have 1 and 39 hundredths. In that particular case, there's no reduction that is possible, so I have my final answer right away. Now that brings us to the more difficult and thought-provoking portion of our lesson. So if it seems pretty easy up to this point, great, but pay attention as I cover this last section, as it is much more difficult to really comprehend and understand. I would even encourage you to watch this portion of the video several times until it makes sense to you. We're going to change from a repeating decimal into a fraction. So the first thing I'm going to do is I'm going to let a value, a variable such as n, equal my original decimal value. In this case, 0.56 with the 6 repeating. We're next going to multiply both sides of the equation by some power of 10. Usually the same power as we have digits repeating. So if I have one digit repeating, such as in this example here, I'm probably going to multiply by 10. If I have 2 digits repeating, I'm going to multiply by 10 squared, or 100. 3 digits repeating, I'm going to multiply by 10 cubed, which is 1,000, and so on. What we want are the repeating digits to be able to line up when we do subtraction, which will be a little bit later on. and we want at least one non-zero digit before the decimal point. So in my example, I have n is equal to 0.56 repeating. So we are going to multiply by a power of 10. So if I multiply this side by 10, that gives me 10n. If I multiply this side by 10, that gives me 5.6, again with the 6 repeating. Now my next step is to subtract a value of n from both sides of this equation. So if I take 10n and I subtract n, that's going to give me 9n. And so when I do that subtraction, I get 9n. If I take the 5.66666, and it keeps on repeating, and I subtract the value of n, in this case my decimal value, 0.56666 repeating, those repeating sixes are going to end up canceling each other out, which is what we want, because now we no longer have a repeating decimal, but a terminating one. So we have 9n is equal to 5.1. Then, what we're going to do, I simply copied this from the last slide, we are going to solve for n from this equation. So to do that, I'm going to divide both sides by 9. That gives me 5.1 over 9. Now remember, our goal is to get this into a fraction. So I don't want to take my calculator, type in 5.1 divided by 9, because that will get me back to where we started. We want to keep it as a fraction. However, we do not want a decimal in a fraction as our final answer. So what I'm going to do in this case is I'm going to multiply my fraction by 10 over 10. That would give me 51/90ths. There is an equivalent fraction of our original 5.6 repeating. Now the last step is I want to make sure that it does not reduce, because I want to reduce it if it's possible. So in this particular case, I can reduce it by a factor of 3. So if I divide by 3 over 3, I get 17/30ths. So 17/30ths is equivalent to 0.56 repeating. These are easy to check your answers on. On a calculator, if you take 17 and divide by 30, you should get 0.5666 with the 6 continuing to repeat. You know you have a correct answer. That's a great way to check. The only thing it's not going to allow you to check is whether you've reduced completely or not. But at least you know you have an equivalent fraction in relationship to your original decimal. So let's try another one, because if you're like most students, your head is like, what just happened? I don't know. So we're going to walk through another example. Let's say we have 0.453 and just the 3 is repeating. So I begin by setting n equal to 0.453. I am then going to multiply both sides of this equation, the n equals 0.453 repeating, by 10. I could also do 100 just to show you that it is going to work out. But you've got to be careful about over multiplying. In this particular case, I just have one digit repeating, the 3 repeating. So if I multiply by 10 or 100 or 1,000, my repeating decimal portion is always going to line up. If I have 2 decimals that are repeating, I need to multiply by 100. If I multiply by 1,000, that would not allow me to line up my repeating decimals. So you want to make sure you line them up. As an example, if I have, let's say, 0.56, where both the 5 and the 6 are repeating, I can set n equal to that. Well, if I multiply by 100, then that means 100n would be equal to 56.56 repeating. But notice that when I line up my decimals and I can do my subtraction, my repeating portion is lined up. If I take my original number of 0.56 and let's say I multiply by 1,000, then that is going to give me 565.656565. These repeating values are not lined up. Notice that the 5 and the 6 and the 5 and the 6 are over each other. I want the same value to be over itself. So the 6 over the 6, the 5 over the 5. If you get a situation like this, you need to change what you're multiplying by your n. You want them to be lined up. So you'll simply have to start over again and rework it. As a general rule, however many digits are repeating, that's the power of 10 that you want to use. So in this case, it's still going to line up, so I'm going to keep on moving. Now I'm going to subtract from this second equation a value of n. So 100n minus n gives me 99n. And then if I take 45.3 repeating and I subtract the 0.4533333, I'm going to get the 44.88. Now, for many students, it's easier to see the subtraction over each other. If I have the 100n, which is equal to 45.3 repeating, and I subtract n from this side and an equivalent of n from this side, which is 0.453 repeating, I can carry out this repeating 3 several more places so that these 0.3 repeatings are over each other. So I have 100n minus n, which gives me the 99n, is equal to, if I subtract 3 repeating from 3 repeating, those cancel out. And then I have 45.33 minus 0.45, and that would give me the 44.88 that you see over here. My next step is then to divide both sides by the 99. That gives me n, which is what my original equation is equal to 44.88 over 99. Now once again, I have decimals in a fraction, so I'm going to multiply by 100 over 100 to get rid of my decimals. That gives me 4,488 over 9,900. If I reduce that, keep on reducing until you can't reduce anymore, you'll get 34 over 75. So on a calculator, if you take 34 and divide by 75, you will get our original decimal of 0.453. And therefore, you know you have a correct answer. So let's try 0.06 repeating, where both the 0 and the 6 are repeating. Do you remember what the first step is? The first step is to set n equal to our original value. What is the next step? The next step is to multiply both sides of my equation by some value that is going to line up my repeating digits. I have 2 digits repeating here, the 0 and the 6, and so I want to multiply by 100, which is 10 to the second power. So that gives me 100n is equal to 6.06 repeating. What's the next step? The next step is to subtract the value of n from this second equation. So 100n minus n is 99n, and 6.06 repeating minus 0.06 repeating gives me simply a value of 6. So I have 99n is equal to 6. I want to solve for n as a fraction, so if I divide both sides by 99, I get 6/99. I have a fraction. In this particular case, I don't even have a decimal in it. So I can skip that step of getting rid of the decimal and go straight to reducing. I can reduce by a factor of 3. That gives me 2 over 33. On a calculator, I can check my answer by typing in 2 divided by 33, hitting equals, and I should get 0.06060606, and it continues on in that fashion. So I know I have a correct answer. What about 0.27, where just the 7 is repeating? First step, set n equal to my original value. So n is equal to 0.27 with the 7 repeating. The next step is I'm going to multiply by a power of 10 to get my repeats to line up with each other for subtraction. In this particular case, I can use a 10. So 10n is equal to 2.7777, and the 7 keeps on repeating. Now I'm going to subtract the value of n from both sides of that equation. So 10n minus n gives me 9n. And then 2.7 repeating with a 0.27 repeating, subtracting, we get 2.5. Again, if you need to line them up vertically, that is usually the better way of going about it. If I then divide both sides by 9, I get n is equal to 2.5 over 9. I have a decimal inside my fraction that I need to get rid of, so I'm going to multiply by 10 over 10. That gives me 25 over 90. And then I can reduce that mainly by a factor of 5, which gives me 5 over 18. And that is my final answer. If I take 5 on a calculator and divide by 18, I'll get 0.277777, and it continues on that way. Let's try one more. This is a very large example. We have 0.714285 repeating. All of those digits are repeating. So I'm going to set n equal to that value. I am then going to multiply both sides by 1 million because I need 6 zeros in order to get the repeating portion to line up when I do my subtraction. So I now have a million n is equal to 714,285.714285. Now when I subtract my value of n from both sides, I get 999,999 n on my left side and 714,285 on the right side. To solve for n, I've got to divide by that 999,999, and that gives me 714,285 over 999,999. This is large numbers. Reduction is much more difficult. You probably won't be able to find the greatest common factor right away. Prime factoring is a lot of time, so you want to likely look for things that you know you can divide by and just keep on dividing until you can't divide anymore. When you prime factor, this is what it would look like. In this particular case, I can cancel out this set of 3s, this set of 3s, this set of 3s, this set of 11s, this set of 13s, this set of 37s, and that leaves me with simply 5/7. If I take 5 and divide by 7, I do indeed get that original number. Now, I would like to cover one more thing, but I want to preempt it with a warning. This only occurs in certain situations, and so if you see that situation, you are more than welcome to use it. If you doesn't fit in that situation, you cannot use it. You will get wrong answers. So be very, very careful. In fact, every year as I teach this, I contemplate, should I even show students this particular method? But it does save a huge amount of time in the situations that it works. The first thing you want to look for is it going to work given the number that I've been given? This is an example where it will work. What you're looking for is, are all the numbers of my decimal repeating? In this particular case, every single value behind the decimal point is a portion of the repeating portion. So if this were 0.71, where just the 1 was repeating, it would not work. The entire decimal portion has to be a repeating portion in order for this method to work. I cannot stress that enough. If you have any other scenario, this will not work. But when you have this scenario where it will work, it will save you a lot of time. So in this particular case, I can skip a lot of this if I recognize that my entire decimal portion is repeating. So here's what I can do. I can take that entire decimal portion and write it as my numerator, 714285. And then in my denominator, I am going to write the number of 9s equal to the number of repeating digits. Here I have 6 repeating digits, so I'm going to write 6 9s down in the denominator. And then I can reduce. If you'll notice, this number right here is exactly what we have right here. But again, it only works when your entire decimal portion is repeating. If you see that scenario, you can skip all of this and go straight down to here. I hope that was helpful for you. Again, re-watch a portion of this video that deals with the repeating decimals and how to get rid of them and change them into fractions. If you don't understand something, eventually it'll work. It takes practice, but after a while, you'll get the hang of it, I am sure.